The name of this compound here is either 4-methyl benzoic acid, or alternatively you could use para for the location of the methyl group. B is ortho amino, or you could say 2-amino benzoic acid, and its common name is anthranilic acid. For 7, we numbered the longest chain, with carbon 1 being the carbonyl carbon of the carboxylic acid, and the longest chain is a 7-membered, so it's a heptanoic acid. We changed the E suffix with oic acid for the carboxyl group. Carbon 4 has a benzyl group. Carbon 7 has a cycloheptane ring, so as a substituent it's cycloheptyl. Stereochemistry is R at carbon 4. So this is alphabetically 4-benzyl, 7-cycloheptyl, heptanoic acid. It's implied that the oic acid location is at carbon 1. D, the functional group that we have at D is a carboxylate ester. Remember, always number carbon 1 as the carbonyl. You do not number the oxygen. This is the alkyl group bonded to the carboxylate ester. So the alpha carbon is 2, 3, 4, 5, 6, and 7. So this is also a heptanoic acid derivative, so it's a heptanoate. And carbon 6 has 2 methyl groups, so this will be a 6,6-dimethyl heptanoate ester. And the alkyl group bonded to the carboxyoxygen is a 4-carbon isobutyl substituent. So this is named isobutyl space 6,6-dimethyl heptanoate. E is the salt of benzoic acid. Ammonium is the countercation, so this is ammonium benzoate. Note that carboxylic acid salts, the carboxylate, are named similarly to esters and vice versa. This would be the phenyl ester of acetic acid, so this is phenyl acetate. G has a common name, phthalic acid, because it's derived from naphthalene. And you can also call this ortho benzene dicarboxylic acid. Or benzene 1,2-dicarboxylic acid. Here we want to provide a reasonable mechanism for the following transformations. So A is actually called, it has a special name to this reaction. It's called bromolactonization. And the mechanism will redraw the starting material. It's this cycloalkene with a methylene carboxy. So you've got a carboxylic acid. And that was it on the structure. And we treated this with bromine and methylene chloride. And we got this, so there was a methyl group missing. We got this bromolactone. Oops, excuse me. This was okay. There is no methyl group. I don't know why I did that. And it's called a lactone because we have a cyclic ester. Our byproduct was hydrogen bromide. So let's try pushing arrows to show the production of product. So the first step, remember that the alkene is a nucleophile in electrophilic addition to give the bridged bromonium ion. Here let's show it as being down so that it's then susceptible to attack to cyclize. So the oxygen, really we ought to show the carbonyl oxygen attacking the bridged bromonium ion instead of bromide. So this is an intramolecular substitution. And so the carboxyl group attacks the bridged bromonium ion. That strained three-membered ring opens up, and now we've formed the carbon-oxygen bond of the lactone. And so really we ought to have used the carbonyl oxygen. That way this is resonance stabilized. And then the last step is deprotonation of the dioxocarbocation. Also here we could describe it as the protonated lactone, and we get our product. Deprotonation by a bromide ion shows the production of HBr. The next mechanism is the hydrolysis acid catalyzed hydrolysis of N-ethylbenzamide, our secondary amide, to give back the carboxylic acid, benzoic acid, and ethylammonium chloride. Byproduct. Okay, so our mechanism we could say is nucleophilic acyl substitution, and we could specify that this is acid catalyzed hydrolysis. And so the first step, remember that we are always going to protonate a carboxylic acid derivative at the carbonyl oxygen. And we could show our acid being hydronium, because really hydrogen chloride dissolved in water gives you hydronium chloride. We then have the resonance stabilized protonated amide. This activates the carbonyl by making the carbon more electrophilic now that you put a positively charged proton on it. In order to get to product, we know we're going to have to break the carbonyl nitrogen bond, and we're adding water to have a new oxygen in place. So water is going to add to the carbonyl. We get our first form tetrahedral intermediate. And right now our water that just added is still the best leaving group. So if you want to prove this to yourself, pKa of this conjugate acid is around 36 to 40. pKa of water is 15.7. pKa of a benzene is 43. And then the pKa of hydronium is negative 1.76. So our best leaving group is still the water that added. So we have to shuttle a proton around to the nitrogen in order to break the carbon-nitrogen bond. then that way we would have the conjugate acid being ethyl ammonium chloride, or just ethyl ammonium rather, and its pKa being in the vicinity of 11. Of course, we never break the carbon-carbon bond here. pKa 43, phenyl is never going to leave. Hydroxide, we always say, is a poor leaving group. So to stack the deck, we have to have an intermolecular proton transfer event. And we might as well go ahead and draw that out explicitly, although you could just draw the structure, but water will pick up the proton from the positively charged oxygen that just added as water, and so you would regenerate the acid catalyst at that point. And then the nitrogen we would want to protonate so that it then becomes the best leaving group. So the nitrogen lone pair gets protonated by hydronium. Now you get the tetrahedral intermediate that will actually collapse to give you the benzoic acid. And we could show the collapse pushed by either oxygen, but here this oxygen and carbon double bond is reforming and at the same time spitting out ethylamine, and this is being helped by the hydrogen bonding in solution. So this is collapse of tetrahedral intermediate. We're losing ethylamine. Which then immediately would deprotonate our protonated carboxylic acid. To give us our products. And so the last mechanism question was to show what we would describe as Gabriel synthesis. Let's name B before we move on as acid catalyzed. Acid catalyzed hydrolysis of an amide. But here in the Gabriel synthesis, hydroxide will remove the acidic proton of the imide. So then the imide conjugate base, so where we have the negative charge on nitrogen, then acts as a nucleophile of phthalimide. Attacks ethyl bromide in an SN2 fashion to give the alkylated phthalimide, and then hydrolysis to phthalic acid and ethyl ammonium bromide. Work up with base, then free bases, the ammonium salt to ethylamine free base. to continue with fill in the blanks, here we have a primary alcohol reacting with bleach and acetic acid. This is a mild oxidation to oxidize the I'm going to zoom out for a second. This oxidizes the primary alcohol to the aldehyde. There's no water, so you do not get the hydrate, which would be further oxidized. So we've got 1, 2, 3, 4, 1, 2, 3, 4. Here's the new carbonyl. So there's our aldehyde. And then treated with chromic acid, it would oxidize the aldehyde, continued oxidation to the carboxylic acid. Of course, you could have started from the primary alcohol to get here directly by just treating this originally with chromic acid, but this was just instructive to show the difference in oxidation reagents. Then with thionyl chloride, you convert the carboxylic acid to the acid chloride. Treatment with excess diethylamine then would give you the diethylamide. Tertiary amide. And then the last step, which would give you hints, is acidic acid-catalyzed hydrolysis of the amide to the corresponding carboxylic acid with loss of diethylammonium chloride. B, we have an alpha, beta, gamma, delta. We have a delta valorolactone. The first step is base-catalyzed hydrolysis followed by workup. So you are going to cleave the carbonyl oxygen bond by the addition of water. You can work through that mechanism independently. Try and keep the atoms in place to convince yourself that you didn't lose any. It's the electrons that are doing the dirty work. And then thionyl chloride is in excess, so this will convert both the carboxylic acid to the acid chloride and also the primary alcohol into the alkyl chloride. Treatment with aniline, one equivalent. This demonstrates the fact that acid chlorides are more electrophilic and more reactive than primary alkyl chlorides. So from the acid chloride plus this amine, we get the amide. And then lastly, a good nucleophile such as potassium thioacetate in a polar aprotic solvent like DMF promotes nucleophilic substitution at the sp3 hybridized carbon-chlorine bond. So our final product is both a thioester and an amide in the same molecule. Predict the product. Potassium formate plus benzoyl chloride formate ion acts as a nucleophile, and we end up making the mixed anhydride. When benzoyl chloride is met with isopropyl alcohol, you make the benzoate ester, specifically isopropyl benzoate. When this acid chloride is met with an excess of benzolamine, you make the amide. Your byproduct would be benzylammonium chloride. D, treatment of cyclohexane carboxylic acid with thionyl chloride converts the carboxylic acid into the acid chloride. And then treatment of this acid chloride with phenol gives you the aromatic ester. And note that the parachloro group will still be intact. Sorry, I accidentally started to draw the ketone. Let's redraw this. I'll get my white out. All right. Let's draw it over again. E, this is again acid catalyzed hydrolysis of an amide. So we get out benzoic acid, and since it's under acidic conditions, we get the free carboxylic acid and our ammonium salt. Here, this was a bonus. This was actually performed at our university. Thionyl chloride, we get the acid chloride from this step, and then in the second step, pyridine actually forms this N-acyl pyridinium as orange needles, and this is also reactive, and so when it sees this alcohol, it makes an ester in the third step. Spits out pyridine, and the final product would look like this. We talked about this in lecture, which is why it was in the notes. To continue, here we have phenylacetic acid and acidic methanol with dehydration, and it makes the odor of honey, so this is a hint that we make an ester. Remember that we said esters are generally pleasant smelling, and in the first semester laboratory we made isopentyl acetate, the odor of bananas. And so we would definitely categorize this as Fischer esterification, named after Emil Fischer. And here we're making the methyl ester of phenylacetic acid, so this would be called methyl phenyl acetate. H, phosphorus trichloride, converts the carboxylic acid, butanoic acid, to butanoyl chloride. So this reagent acts similar to thionyl chloride to convert this into the acid chloride. And then next, treatment of the acid chloride with ethanol provides the carboxylate ester. I, with one equivalent of acetyl chloride, this mechanism would give a mixed anhydride, and this actually catalyzes the formation of a cyclic anhydride. So we would form a 1, 2, 3, 4, 5-membered ring. We would form a tetrahedral intermediate, so my arrows are really cheating. It goes up on the oxygen and then it would crash back down to spit out acetate. So these arrows are cheating. Try and follow the mechanism on your own, but this is a 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 membered ring. To give a cyclic anhydride, and you might want to number this to keep track of your atoms, and on carbon 2 the ethyl group still remains. So we would say that this is a derivative of a dicarboxylic acid, 1, 2, 3, 4, 5 carbon dicarboxylic acid is a glutaric acid. So this would be a glutaric anhydride, 2 ethyl glutaric anhydride. J is acid catalyzed hydrolysis of this amide and this methyl ester. And it would also protonate the carboxylate salt into the free carboxylic acid. So our products, plural, would be this carboxylic acid. We would then get the ammonium salt of phenylalanine and the alcohol from this methyl ester, which is methanol. And then this is one reason why people claim that aspartame, artificial sweetener, is toxic, because your body can hydrolyze this to methanol, which then would be further oxidized to formaldehyde, which is very bad for your liver. K, the first step, is base catalyzed hydrolysis of this methyl ester to give you benzoate and methanol. Second step is a dilute acid workup to give you the free benzoic acid. And then the third step is thionyl chloride to give you benzoyl chloride, the acid chloride from benzoic acid. L, here we have an acid chloride plus a thiol, so here we're going to get a thioester. M, here we have acetic anhydride plus methylamine, and so here we're going to get the amide and an equivalent of an acetate salt, and specifically it would be methylammonium acetate. We needed two equivalents because in the reaction mechanism, methylamine will, in addition to acting as a nucleophile in the first step, also act as a base. Here we have a lactam, and if we wanted to classify this lactam, this is an alpha, beta, this is a gamma lactam, and it's the gamma lactam of a 1, 2, 3, 4, 5, 6 carboxylic acid. So this is gamma caprolactam. And in IUPAC, you would say that this is 1, 2, 3, where the ethyl group is. So this is 2-aza, 3-ethyl cyclopentanone. This name is misleading because this is not a ketone. It is a cyclic amide known as a lactam. Nevertheless, acid catalyzed hydrolysis hydrolyzes the amide to give you the carboxylic acid, the ammonium salt, and stereochemistry has not, remains intact. O, here this is called orthodihydroxybenzene. It also has a common name known as catechol plus phosgene, which is a toxic gas. And what happens here is that you form a derivative of carbonic acid. And in terms of its mechanism, what would happen is that one of the phenolic oxygen atoms would attack the carbonyl of phosgene, spit out chloride after collapse of the tetrahedral intermediate to get this chlorocarbonate, and then the process would repeat itself, but in an intramolecular process, with loss of HCl to give you the carbonate. P, this is a alpha, beta, gamma lactone. If we wanted to name this an IUPAC, this would be 2-oxa, 3 with a 3-isopropyl. So this would be 3-isopropyl, 2-oxa cyclopentanone. And this is base catalyzed hydrolysis. And so we would hydrolyze the carboxylate ester, the cyclic carboxylate ester. And so since it's under basic conditions, we would still end up with the carboxylate salt. And go ahead and number your chain to convince yourself that this is what you have. Right? And so if you wanted to name it, this would be a 4-hydroxy-5-methyl heptanoic acid salt. Q, here we have a mixed anhydride. And what's nice here is that you have to decide which carbonyl it will attack. And our best leaving group is going to be acetate rather than attacking this carbonyl and spitting out an alpha hydroxy ketone. So it's best for the base to attack here, form a tetrahedral intermediate, collapse, and it would not be best to do this part, because this would be pKa of its conjugate acid around maybe 15. Whereas the pink arrows show the correct process, where this is attacking the carbonyl. Oh, you know what? This is not, sorry, I misspoke. This is not mixed anhydride. I went too fast. This is an ester. It's an ester of acetic acid. And so far what we've learned is that we'll have base catalyzed transesterification. So this does occur. You will spit out the alpha hydroxy acetone. And so this is the alcohol of your original ester, and this is the methyl acetate that you created via this base catalyzed transesterification. Here we have a cyclic anhydride, and this is acid catalyzed, so we're going to protonate one of the carbonyl oxygens and then form the ethyl ester and the carboxylate leaving group, which would then be protonated under the reaction conditions to give you the carboxylic acid. So here we would want to rationalize it. If we attacked this carbonyl, our leaving group would be benzoic acid, so pKa around 4.21, whereas if we attacked here, we would kick out a phenyl acetic acid, which has a higher pKa value. So it would stand to reason that we would form the ethyl ester here from this carbonyl of the anhydride to spit out the better leaving group. This is a challenging question. And then it's possible to do a Fischer esterification as well, but generally we choose sulfuric acid for that type of Fischer esterification. So most likely you would get this as your major organic product. S, you have a secondary amine, and a secondary alcohol in the presence of acetyl chloride. So this will either create the amide or the ester from acetyl chloride. And so we can show, firstly, the amide. Nitrogen atoms are more nucleophilic than oxygen. They're more stable with a positive formal charge than oxygen, and at least in the mechanism. And our other product would be the acetate ester. And since we are generating HCl, we would have this be protonated. Here, T, we have an alcohol and a carboxylic acid tethered in the same molecule. So here we're going to complete a Fischer esterification reaction. So we're going to protonate the carbonyl oxygen to activate the carbonyl. This then swoops down to add in an internal SN-AC reaction. So here we're going to form a 1, 2, 3, 4, 5, 6-membered ring. So we get a cyclic ester as a lactone. And the ethyl group will still be bonded to the carbon that had the OH. So that's this carbon here. And so we can say this is an alpha, beta, gamma, delta, epsilon, zeta. So we wouldn't continue for that because we usually don't go past epsilon. And so we would say that this is 3-ethyl, 2-oxa, cyclohexanone. The last couple reactions, here we're going to have an intramolecular transesterification. So you protonate the carbonyl oxygen, the nucleophilic OH swings over to do an intramolecular SN-AC, spits out ethanol, and so your product will be a 1, 2, 3, 4, 5, 6-membered ring. And your cyclopentane will still remain intact, and so that will be here, and the stereochemistry is still cis on now this bicyclic ring system. This is a challenging question as well. This is good for practice, but you probably will not see something like this on the exam. Here we have acid catalyzed hydrolysis of this ester. The nitro group is not going anywhere, so we're going to spit out paranitrophenol, and we'll end up with the dicarboxylic acid. Here we have 4 methylenes, so here we go, 1, 2, 3, 4. So this is, oh my, such good apple pie, so this is adipic acid, plus paranitrophenol. And then the last part were bonus mechanisms. So these were challenging, but let's show how we can get to product. So let's redraw our reaction. So again, this is another derivative of a carbonic acid, and this is called a carbamate. So it's not just an ester and an amide, it's called a carbamate. And here we have HCl as our acid, and we're going to lose water. And our product is this spirocyclic system. Note that the carbamate is still intact. And so for this mechanism under acidic conditions, the first thing that you're always going to do, protonate the most basic lone pair. Also, this is going to make sense in our product. We're then going to develop a tertiary allylic carbocation. We would draw a resonance structure where we move these pi electrons to reveal a positive charge at this carbon instead. And this more closely resembles our product, so this makes sense to do such a thing. And here we're going to use the nitrogen lone pair to form our 5-membered ring. This is 1, 2, 3, 4, 5. So the nitrogen nucleophile attacks the positive charge to form a 5-membered ring. And then the last step is the water that it displaced. So we forgot to show that after protonation, to get the oxonium, water also left. So then this is our base. Later along the line in the mechanism, we'll deprotonate the protonated carbamate to give you the neutral product. B, another challenging mechanism. So here we have basic conditions. To get this as our structure. And so what's going to happen here? So superficially, what happened is that this oxygen is going to attack this carbonyl. So we're forming this 5-membered ring, and then it spits out beta trifluoroethanol as the leaving group. So what we could show here for this process to occur is deprotonation of the amide. Loss of the proton, we can then resonate the negative charge onto the oxygen atom, which is going to form the new carbon-oxygen bond that we need to show. So this does an intramolecular substitution. Let's go ahead and draw the actual tetrahedral intermediate. And then our best leaving group is now trifluoroethanol. So this lone pair comes crashing down to form the carbon-oxygen double bond of the lactone and spits out. This is a fantastic leaving group to give you our product. And so the pKa of trifluoroethanol, I believe, is in the vicinity of around 12.5. So this is certainly our best leaving group. And then the last mechanism is treatment of catechol with potassium carbonate, and this deprotonates the phenol. We could show one of the phenoxides at a time, and we're treating it with the alpha beta dibromo methyl propanoate. And here let's show SN2, the less sterically hindered bromide, or we could have also chosen the alpha carbon, because this one's certainly also very electrophilic. So this was an SN2. And then we would show the potassium carbonate again pulling off a proton of the phenoxide. And then this is going to form a 1, 2, 3, 4, 5, 6-membered ring, which is what our product shows. And this would be the product of our first step. With catechol, potassium carbonate, and let's go ahead and name this. This is methyl 2,3 dibromo propanoate. And then the second step is base catalyzed hydrolysis of this methyl ester to give you the carboxylate. And then the very last step is the acidic workup to give you the free carboxylic acid. And our byproduct is, of course, methanol that we just hydrolyzed from the methyl ester. So that's it for this problem set.